There is no doubt that entropy, at least as classically defined, is a mysterious thing. In a seemingly arbitrary decision, we define entropy by saying that its change during any thermodynamic process equals the heat transfer for a reversible path divided by the temperature. Classical thermodynamics then goes on to declare audaciously in the second law of thermodynamics that entropy is a state function that always increases for the universe as a whole in the course of any spontaneous change. Another thing we can say about entropy is that it is somehow related to disorder. This idea comes from our intuitive notion that spontaneous processes always increase disorder. For example, we know intuitively that energy always flows as heat from a warmer body, in this case a block of red-hot metal, to a colder body, in this case the surrounding air. This dissipation of energy represents a loss of order because before it occurs, the energy is concentrated in the warmer body, while after it occurs, the energy is spread out more evenly. Other examples of spontaneous processes that increase disorder are the spreading out of a gas to fill the available space, and the conversion of your neatly made bed into a messy bed. So all these processes somehow lead to an increase in disorder. And since they also lead to an increase in entropy, this suggests a link between entropy and disorder. This link is hard to pin down based on the classical definition of entropy, but in the next lecture, when we discuss something called the statistical definition of entropy, we'll see a much more concrete link between entropy and disorder. You may think it's nothing short of audacious to declare that the ratio of a path function to an intensive state function is itself a state function. Where's the proof, you may ask? Well, we don't really need to prove that entropy is a state function. We can just accept this notion as a part of the second law of thermodynamics. After all, by saying that entropy of an isolated system increases as the result of a spontaneous change, we are implying that entropy is something with a definite value that only depends on the current state of the system. And this is the definition of a state function. Nonetheless, as shown in this slide, it is possible to prove that entropy is a state function. This proof invokes the classical definition of entropy and the first law of thermodynamics. It may also seem audacious to declare that the entropy of an isolated system always increases as the result of a spontaneous process. However, this declaration is amply demonstrated by the success of classical thermodynamics as a discipline, and so doesn't need to be proved. But once again, we can offer something of a proof in the form of the Clausius inequality, which is derived in this slide. Once again, this proof invokes the classical definition of entropy and the first law of thermodynamics. So once we define entropy as Q reversible over T, we can prove that the entropy of the universe always increases in the course of any spontaneous change. Therefore, we can think of these two things as alternative and equivalent statements of the second law of thermodynamics. Finally, I want to remind you that the second law of thermodynamics does not say that the entropy of a system can never decrease in the course of a spontaneous process. It only says that if the entropy of a system decreases, the entropy of the surroundings must increase such that the overall entropy of the universe increases. That explains why a disordered ball of cells can turn into an intricately structured human being.